My name is Laszlo Székelyhidi. I'm chairing this session. This is the PDE thematic session, and we have a fantastic lineup of invited speakers. So, and I'm very happy to present our first speaker today, Tristan Buckmaster from Princeton University, and he will speak on new results related to singularities for compressible fluids. So please, Tristan.
Thank you. Thank you for the introduction. Thank you to the organizers, for Laszlo and Vlad, for inviting me to speak. So I'll be talking about two different results. The first part of the talk will be results with Steve Scola and Vlad Vicol, and the second part will be with Gonzalo Cal Labora and Javier Gomez Serrano. So in both parts, I'll be talking about the Euler equations. And so this is the compressible Euler equations. This is the full non-isentropic Euler equations. So we have the conservation of momentum, conservation of mass, and conservation of energy. So here, U is the velocity, rho is the density, P is the pressure, and E is the energy. And you can also write this in terms of the entropy by replacing the conservation of energy by the transport of, say, specific entropy. So this equation here, and then the pressure law is given by this law here, where gamma is the abiotic exponent greater than 1. So to give an idea, for air, it will be 1.4. The sound speed can be related in terms of the pressure and the density by this law here. So I want to talk about two different types of singularities that can form for the compressible Euler equations. So one is the shock waves. So this is the prototypical singularity that you see for the Euler equations. It's the one that always occurs when you do simulations. It occurs when the speed of a disturbance exceeds the local speed of sound. Mathematically, one can sort of divide up the problem into two parts. One is shock formation, and the other is, so shock formation is before the shock occurs, and then development of the shock, which is developing the shock past the first singularity. And I'll talk about both those aspects. And the other thing other type of singularity I want to talk about is implosions. So implosions are actually classical and go back to the work of Gödeli, and I'll talk about that in the second half of the talk. So this is back in 1942. But typically one is interested, or in physics literature, typically one talks about imploding shock solutions. So the singularity has already occurred, a shock does occur, and then the shock itself implodes. But recently, there's this recent work by Merle, Raphael, Rodiansky, and Seftel, where they show that there exist solutions which are smooth up until the singularity, and that singularity is an implosion. So this is a new type of singularity. These are not stable like the shockwave singularities. Of course, the classical ones are more stable, the ones where you have a shockwave that occurs first and then implosion happens, but one where you have smooth solutions up until the singularity, this is not, this would be very difficult to observe sort of numerically or physically, but I'll talk about more of that later. So first, let's start with shock formation. So let's, why is that not working? Okay. If I switch to this one, it should. Okay, so this is a picture of shock formation and development, actually. So this is I'll talk about what W is later in the talk, but it's a fluid variable. So a shock occurs, and then this is just at the time of the shock occurring. So you see a shock occurs, and there's actually a couple of other discontinuities that are difficult to see. There's two of them here. These are called weak discontinuities, and I'll talk about them in the talk. So they look like little blips, but they're actually important. Okay, and so results, mathematical results in terms of shock development. So there's the work of Christodoulou and Christodoulou-Mao, where they show in the 3D isentropic irrotational setting the formation of a shock. So in particular in the irrotational setting, you have that the it just becomes a wave equation because you remove vorticity, so it somewhat simplifies the equation. And they're dealing with the isentropic case. So in follow-up work building on this framework, Luc and Speck proved in the 2D case that you can also have shock formation, and in this case with non-trivial vorticity. And then more recently in the work with Steve and Vlad, we showed first in azimuthal symmetry that you can have shocks forming and you can have non-trivial vorticity. So one key difference between, say, azimuthal symmetry, where it's angular, instead of, say, radial symmetry or spherical symmetry, is that you can have non-trivial vorticity. Also, we give a full description of the self-similar profile at the singularity. And so this sort of framework was built upon, and we were able to solve the full 3D isentropic problem with non-trivial vorticity. And we're also able to give a precise description of the self-similar profile. And we extended this further to the full 3D Euler, where you have non-constant entropy. And that sort of gave you the full picture for the formation. And there's been just a recent paper in arXiv by Luc and Speck, where they also study the full 3D Euler, but they also consider the case where the solution is non-generic. And I'll talk about what it means to be generic. Okay, so I'll give you a couple of videos of what this looks like. So this is an azimuthal shock. So the shock is, we disregard, because it's symmetric. We have this azimuthal symmetry. All the dynamics is described by the angular variable, and so we just consider annus of the solution. And you can see here a shock forms. Okay, and this is what we prove. And in the generic 2D case, we have a shock forming here. So we do it for 3D, but it's impossible to visualize the 3D one. So this is the density, and a shock forms at the singularity happens at a single point. And this is the stable phenomena. And so this is actually what I meant by generic. Okay. Now back to this. Okay, now I want to talk about, so that was shock formation, and I want to talk about shock development. So after the first singularity. So in a thesis by Landau, wonderful thesis, she proved the existence of shocks for 2x2p systems, and uniqueness follows by typing Liu, and there's follow-up work by Chen Dong, Kong for generalizations of this work. This was improved by Yin, who showed that so this doesn't include Euler, but it was improved by Yin, who showed for spherically symmetric Euler there exists weak solutions past the formation, although there's no description of weak discontinuities, which I'll describe in the next slide. Christodoulou Lisbach showed, also considered the same setting, except they considered isentropic Euler for the formation part, and they considered a restricted problem where they don't allow entropy production after the singularity, after the shock. And so they considered a development, but it's not actually a weak solution to the Euler equations. And so this should be multi, and this shouldn't be, so there's typo here, this should be just Christodoulou. He considered the multi-dimensional case, the irrotational isentropic development, and then this restricted problem where you don't allow, so even if you start with irrotational isentropic data, after the shock forms is well known classically, vorticity is created and entropy is created. And so you can't stick within this framework after the first singularity. And this is what this restricted problem does, is it kind of restricts to this framework. Although what you get in the end is you don't get a weak solution to the Euler equations. So very recently, this should be Drivas. Sorry, I was copy pasting the one, and this talk is also with Theo Drivas. So this is myself, Drivas, Scholar, and Vicol. Is the development of for the full Euler equation under azimuthal symmetry, satisfying the Rankine-Huguenot jump conditions. And in this case, you get uniqueness of the solution and you get a full description of the weak discontinuities. Okay, to describe this, first we have to describe the Rankine-Huguenot jump conditions. So if we use this notation to describe the jump across the shock, and then you can write the jump in the normal velocity. There's no jump in the tangential velocity. The jump in the pressure, so the density, and the jump in the energy. And here UN is the speed normal to the shock. And so you need, and here, so S is the angular coordinate of the shock. So this is the speed of the shock, S dot. And so this, for a shock, you have to set to get a physical and a weak solution to the Euler equations, you need to satisfy these conditions. Landau and Lifshitz sort of conjectured the existence of weak discontinuities in their book, in the textbook. And so in particular, they show that other than the shock surface, there also exist other surfaces, which are called weak discontinuities, where it's not that the fluid variables are discontinuous, it's more that you have discontinuities in higher derivatives or non-existence in higher derivatives. So this is what this sort of weak means. But in the book, they talked about the existence of such discontinuities, but there's no full description of what these discontinuities are. Okay, and so this work is the first mathematical or physical description of what these discontinuities are after the shock. So this is a pictorial diagram. So this is before the shock. This is in the azimuthal. So this whole theorem is in the azimuthal case. So this is before the shock, nothing goes wrong. This is at the time of the first singularity. So this red line, which is difficult to see, is the shock surface, the shock line in this curve in this case. And then after the shock is developed, you get two other weak continuities. So you get this weak refraction wave, and this blue line is the weak contact discontinuity. And so it's characterized by, so the weak contact discontinuity has a one-sided C1 cusp in the velocity, density, and entropy, and the pressure and normal velocity is C2. And so this is why we sort of, this better behavior for the pressure and the normal velocity is why we call this a weak contact discontinuity. And the weak refraction waves, C1 one-sided cusps on the shock side, and the normal velocity is decreasing in the direction of the motion of the fluid. So this is why it's called a refraction wave. So this is a pictorial description, of pictorial representation of the dynamics of the different curves. So here's the shock curve. So this is when the initial singularity occurs, and this is the weak contact discontinuity, and this is the weak refraction curve. And what you should think of is that kind of these weak discontinuities are kind of memory of the first singularity. So something singular happens here, and you have different trajectories you have different trajectories in the compressible Euler equations, and so with these different trajectories, they carry some of the non-smoothness off here. They're not actually discontinuous like the actual shock is. Okay. And it's important, the four different regions, this region here, this region here, this region here, and this region here, and you have to divide up the different regions. So now I want to switch. So yeah, so I'll just summarize this. So this is like the first description of these weak discontinuities. Okay, now I want to switch to implosion results. So Goodley in 42 showed that there exists self-similar imploding shock waves, solutions to Euler, and I'll describe them in the next few slides. So and there's a whole history of papers that develop on this. So there's I can't list all the references related to this work. But very recently, Mel, Raphael, Rodniansky, and Seftel showed that there exists smooth, attenuated, imploding self-similar solutions for almost every abiotic exponent gamma greater than 1. Now, this adjective attenuated is not a good one. I just created it in order to make a distinction, and I'll make that distinction later, but I have to think of a better adjective for this. So they show it's for almost every gamma greater than 1, although they don't show it for any specific gamma. So there's a bit of complex analysis that goes into the work where they show that something happens for almost every exponent, that it responds to like zeros of the analytic function, and they know that they're distinct or they're discrete, but they don't know where they are. But you can numerically compute these analytic functions and see numerically check whether a certain gamma works. So there's a recent numerical work by Biasi that gave a detailed description of implodings of this imploding solutions corresponding to this framework. And in current work, which is not quite finished, we show that there exists an acute, I'll describe this later, for all abiotic exponents greater than 5/3, and attenuated imploding solutions for gamma equals 7/5. Now, this restriction greater than 5/3 is artificial. This result actually works for all gamma greater than 1, and probably when we publish it, it will be for all gamma greater than 1. But we have to. There's a computer-assisted proof part of it, which will have to be extended if we do it for gamma greater than 1. I'll describe that later. Okay, so the setup For imploding solutions, we will consider isentropic spherically symmetric Euler equations. And so here's U, and here's the velocity and the density equation of velocity, and R, here's the radial, the radius. So we make the following self-similar ansatz. So we make an ansatz for the self-similar for U and sigma, where sigma here is the rescaled sound speed, which can be written in terms of the density. And what happens is that at the time of the singularity, the velocity and the sound speed go to infinity, which is very different than a shock wave. Okay, they stay bounded for a shock wave, but for imploding solution, they go to infinity. So let's set our self-similar variable to be zeta, and if you create this self-similar variable zeta, then you can reduce the whole system into an autonomous ODE. Okay, and then now we can study it using phase portraits. So this is a phase portrait, and I've compactified things so that infinity is here and here. So this is the velocity and this is the sound speed. This is self-similar velocity and self-similar sound speed. Now, to create a solution which is defined everywhere, you have to go from radius 0, which is represented by this P0, and have a smooth curve that goes all the way to P infinity, which is radius infinity. But you can't cross these sonic lines. Then the solution becomes infinite. So you have to go through, there's a critical point, this PC, that you have to go through in order to create a smooth solution. Now, the Gooderly solution, what they did is that they created a solution which goes through this PC. There's two ways to go smoothly through this point. There's one direction this way and there's one direction this way. And the classical solutions, they go through this way, but if you go through here, there's nowhere to go. There's nowhere to get to, you can't possibly get to this P0. You always end up hitting this sonic line. So how you resolve this is that you create a discontinuity, so a shock, and you transport yourself somewhere else, and you create then you can get to this P0. So that's a classical solution. So you have this smooth solution up here, you have a discontinuity which transports you over here. Now, what was done in this recent paper by Mel, Raphael, Radyansky, and Zeftel is they actually created a smooth solution everywhere. And so it's very difficult to do, but it's this orange curve here. And so this is actually hand drawn. It's not. Okay, and let's see how you can create such solutions. Okay, so before I do that, I will mention that. So there was, when they released this paper, there was actually three papers. There's the paper on Euler equation, and there's a paper where they use this to also prove singularity formation for the defocusing NLS, I think in 5 dimensions or more. And they also prove singularities for the density independent isentropic 3D compressible Navier-Stokes equation, which is this equation here. So we have viscosity here, and this is the Lamé viscosity coefficients mu satisfying this condition. So my results with Javi and Gonzalo actually encompass somewhat all three papers, in the sense that the result for the Navier-Stokes relies on a stability. The key thing in the NLS paper is the stability argument, which is used for the Navier-Stokes. So we prove a stability result as well, and we prove we prove singularity formation for the compressible Navier-Stokes, and you could also further use this to prove singularity for the NLS, but we don't cover that case we won't cover that case in our paper. So what they showed is that if gamma is in a certain range between 1 and this number here, then you can create solutions which are asymptotically self-similar and behave like the Euler solutions. And what basically happens is that if you write this in the correct self-similar coordinates, these terms end up having a exponentially decaying factor in front of them. So they can be treated as forcing. So then it's just a matter of stability. And what you do is you show that these solutions are stable modulo a finite dimension. In this case, the modes of instability is quite numerous, and it's not known exactly how many there are, but there is some analysis on the stability in this paper. How long do I have, Lessa?
3 minutes.
3 minutes, okay.
Questions, maybe.
Sure.
Yeah.
So this is the result. And so what we do is we rewrite the equations in terms of Riemann invariance. And so Riemann invariance was also a key. It was utilized in all the stuff I talked about the first half of the talk. So if you rewrite things in terms of Riemann invariance, you end up with another autonomous ODE, except that it's a much simpler equation, because first of all, this ends up being transport equations. And second of all, you remove the singularity at that PC only happens in terms of this DC, this denominator of this dz variable. This goes to 0 at the PC, whereas here both these vanish. So it simplifies the equations. And this is a picture in WZ variables, and the solution will go down here, and it goes through here, and it goes down here. And this picture is in the area where the density is greater than 0. So this is the picture, and so the basic idea is that you Taylor expand, use the autonomous ID to Taylor expand around PC, which you do inductively. And what you notice when you Taylor expand is that you get the nth Taylor coefficient of Z has 1 over n minus k factor in front of it, and k is some ratio between the eigenvalues of the Jacobian of PC written in a different coordinate system. And so this singularity is key in understanding the solution. And in particular, so we restrict so R parameterizes the self-similar scaling, and we restrict this range, and this K that I described before goes to infinity as you go to R star. And so what Merle et al. Showed in their result is they considered the case when K goes to infinity, and then in that case you have to consider an infinite number of Taylor coefficients. But when n is approximately k, you get a sort of singularity forming, and also this coefficient switches sign. And this is the key idea. This is one of the key ideas in proving these solutions. So there's this wiggling that occurs caused by this switching of signs, which allows you to construct this solution. So you can't construct this solution for all R, but you can vary R and show that there's a discrete set of R, which there's infinite number of such variables, such that you get a smooth solution. And so it's like it's a shooting argument basically. And as you vary the R, it either could go up and hit this sonic line here, or it could hit this sonic line here. And you show that it does both, and then there's ones that hit the infinity. So I think I'm basically run out of time. The only other thing is that, so we prove the case. What we do is we prove the case when k is small. And so this is why I said this is acute is because the self-similar scaling is more sharp. And this is the more stable regime. And the sort of attenuated one is the least stable regime where you have a lot of unstable modes. And it's useful because you have this restriction in order to, for the Navier-Stokes equation, you have this restriction in order to make sure that the viscosity is vanishing. And in order to show that, it's best that R is large as possible. So that's why you want to consider these attenuated solutions. And we do that using, again, this uses a computer-assisted proof. I'll probably just, you have to compute sort of numerically 10,000 coefficients with actual error bounds, and then use that to then do an inductive argument to control all the rest of the exponents. But I'll leave it there. Sorry for going over time.
Thank you very much. A very nice overview talk. Thank you, Tristan. Are there any questions? Maybe we have time for a few quick questions.
Do we have a question here? Yes, we have one question. Go ahead, Jeremy.
Okay. Hi, Tristan. It's Jeremy. It's maybe a slightly technical question, but I mean, I wanted to know. So I understand that. So I wanted to know. I mean, the proof for us to construct this solution through what you call PC is quite painful, and I was curious if your argument is significantly simpler, which would be a good news.
Yes, it's a lot simpler. It's a lot easier. It's a lot shorter and simpler. So all the equations are much simpler in these variables WZ. In fact, there's a very good geometric understanding in these W. So these are the sound variables, so the Riemann invariants. So, for example, one way to think of it is, I wish I had my iPad connected, but if you think of like in self-similar variables, like PC being like the right-hand side of the screen in the radial sort of part, and 0 being the origin, then the Z waves, you can think of it, the Z waves, if you look at the trajectories of the Z waves, then they have a fixed point at PC, so they don't move at PC. And then it's a unstable fixed point, so they move to the left of PC on one side, and they move to the right on the other side. And what the Z waves will go on the left, they'll go all the way to the origin, which is like radius equals 0, and which they flip over and become W waves, and they go out to infinity. So you have actually, in these variables, you have a very geometric understanding of what actually occurs with these singularities, and the formulas and everything like that is a lot simpler, and the analysis a lot simpler in these variables.
About other questions, or do you have another one? Or sure, go ahead.
But sorry, and just to make sure, you are using the same curve. In other words, you are going. It's not a different. You are going through the same point. That's my impression. But just to make sure, you are connecting the same points, but just a different value of the parameter R, if I understand.
That's correct. So we do one of them where we take the lowest R possible. And that we can prove for all gamma greater than 1, or we currently have it for 5 1/3, but we can prove it all for gamma at 1. And we also do, so it's not like a superset of your result in the sense, it's a complementary result in this sense, because it's different, you end up with different R's, but it's the same as your framework in terms of the solution. And for we have an argument for any gamma less than 5/3 for k going to infinity, which is like your solutions, except that it's done in a different way. You use complex analysis to show for almost everyone. What we do is that we control the signs and the amplitudes of the coefficients up to a certain number, and then we inductively find information on the further ones. And so our proof works, of course, in the neighborhood of 7/5. But the one problem with this argument is that it degenerates as gamma goes to 5/3. So the number of the computational element of it, which is the computer-assisted proof part of it, takes infinite time as gamma goes to 5/3. So you can apply it for any gamma less than 5/3, except that you'll have problems in terms of you won't, go more. You have to compute more and more coefficients as you approach the 5/3. So it's a different way of doing it.
Thanks.
And we just picked 7/5 because that's the coefficient corresponding to air. There was there's nothing special about that number in terms of the mathematics.
I don't see other questions here in the room.
Okay, thank you. I would say, in the interest of time, we thank Tristan and move on to the second speaker. Thank you, Tristan. And then Toan.
Yes, I'm here. Yeah.
Okay.
Okay, maybe let me share the screen.
Yes, thank you. So
you see the screen.
At least I can see it. I hope the people.
We can see also. Yes.
Perfect. Thank you. So so the second speaker is Toan Nguyen from Penn State University, and he will speak on recent progress on Landau damping.
Okay. Yeah. Thanks a lot, Laszlo and Vlad, for the invitations. It's a great honor to speak here. So I like to talk about some recent results with Emmanuel Grenier at Ernest Lyon and Igor Runyansky from Princeton. And also I mentioned results with Daniel Han Quan from Polytechnic and Ferry Crusset at Paris Oxay. All right. And I should also mention the funding that I received for this work from NSF and IMS and Simon. Okay. So right. So the interest is plasma physics. Okay. And in plasma physics, you wanted to understand the dynamics of ions and electrons, and of course you could look at in the fluid model or kinetic model. In this talk, I look at the kinetic model of a plasma, and in fact, I look at essentially the simplest model for the dynamics of electrons. Which is just the transport equations. It's called Vlasov. All right. So you have the electrons density distributions functions, which is F as a function of T, X, and V, and it solves transport equations. All right. And the field is E, which is the electric field. It solves the boson equations. All right, boson equations. And I'm going to look at this problem on the phase space, either on the torus cross R, which the torus here is for X and R is for V, or on a whole space, okay, R cross R, R3 cross R3. All right. And I said this model is the simplest model in plasma physics because you ignore collisions because you are interested in the long-range interactions, and you ignore magnetic field. Let's say speed of light is infinite, and you also ignoring the ion dynamics. All right. Just think about the fact that the mass between the mass ratio between electrons and ions are very, very small, right? And so you are just interested in the dynamics of electrons. Okay, so one here is really the densities, charge densities of ions. And for this model, you could think of this as the Hamiltonian dynamics for particles. So it's just an ODEs, x dot equal v and v dot equal e, right? The electric field, and E is recovered through the mean field Coulomb interactions. Okay, that's how you get boson equations. How you get boson equations. All right, and what is the interest? So the interest is, which is a major open problem, is to understand the last time dynamics of the solutions. All right, you start from smooth initial datums, you get the smooth solution for all time. But what is the last time behavior? And this problem is very difficult because the system is Hamiltonians, so time reversible. You have energy conservations. You have many conservation laws, like OLB norm of F is conserved, just the transport equations. So to understand these questions, the first step is to understand the end states, all right, and to look at what are possible end states would attract the last time dynamics. All right, and you have a lot of steady states. Basically, the any function of Hamiltonians is a solutions. And it's very easy to check that if the equilibrium monotone in terms of the particle energy, then they are stable. Okay, stable in L2. However, this is just the orbital stability, right? You don't know any information of last time dynamics, meaning in last time would it converging to some steady state. In this talk, I will focus on monotone, radial, spatially homogeneous equilibria. Okay, meaning that the equilibria of F star equal a function mu of V only, right? So this is what I call spatially homogeneous. All right, and it's monotone, so mu prime is less than 0. In fact, it's for monotone equilibria, it's necessary that it has to be spatially homogeneous. All right. Okay, so the question is clear, is that if you start near this equilibrium, would the long-time dynamics converging to it? To understand these questions, of course, one has to understand the damping mechanisms, right? The damping, whether you have any underlying damping. And it was a shocking discovery by Landau in 1946. He discovered that the electric field is damped. Okay, it's always damped. Okay, and his result is for Gaussians, and later extended by Penrose to more general equilibrium. Okay, and what is said here that right said here, I think you can see is that the field are always damped. And the rate of damping depending on the wave number, okay, the wave number. And my talk today is to discuss this result and to explain the physical interpretations of these results, and also some recent nonlinear results on these directions. Okay, on these directions. To understand this damping mechanism, the first step is one has to understand the free transport. So the free transport is the one that without electric field. So if you are in the whole space, everything just transported. So at the positions, particle at the positions x and v, it just become x plus vt and v, all right, and just transport it. So if you just look at in the physical space, everything just moving. This picture I drawn is on a torus. So it's on the torus is more interesting to look at the picture at least. Is that suppose that you put the particles that are lying on this let's say red line, then the particles just transported, all right. But because you are on torus, so you mixed, okay. So this is what we call phase mixing. And it's clear that there's no damping for F. That's clear because all OLP are conserved. However, as time, as T goes very, very large, you all mixed. And so if you look at the average in V, you integrate in V, let's say, then you don't see the dependent in X. Okay, so you don't see any dependent in X. That means that the damping is the damping for microscopic quantities, right? Because you don't see any dependent in X. It's just convergent to a constant, which is the average of X, the average of F. All right, so which means that you don't expect strong convergence for F, but it's just a weak convergence. Explicitly, you can do it explicitly, right? Explicitly in Fourier, all right, in Fourier, here K is the wave number, is equal the Fourier variable of X. And you calculate the densities of that, which is exactly the Fourier transform of F initial datum, evaluate at K and KT. And so it's clear that the regularity in V will give you decay in Fourier variable of F, and that dictate the rate of damping. Okay, dictate the rate of damping, which is clear. And for my talk, I most of the time I just focus on the case of analyticities, but just to see the damping. But I would say if otherwise. And so a very quick conclusion from this is that if you are on torus, you have phase mixing and you have exponential damping. If you are on whole space, then you integrate that in K, then you get decay of T-3 for densities. Hence, you get T-2 for electric field. All right. So this is a picture of free transport. Very, very explicit and clear. All right. Now for the Boltzmann, which is the system that I wanted to discuss, you have the free transport plus the electric field, right? Plus the electric field. And so the point is that you wanted to see, you wanted to compare the dynamics of free transport and the dynamics of electric field, right? Free transport and electric field. You wanted to understand that ratio. And the key quantity to look at is this function. And this function is nothing but the ratio between the electric force and the free transport. Okay, you integrate in V because E doesn't depend on V. So this ratio is very important. And one is so you wanted to compare this ratio with the one. All right. By looking at that, you see immediately three regimes. Yeah, three regimes in this ratio. Okay, in this ratio. From here, I take lambda and K. This is just the usual way to look at the resolvent, right? So you have three regimes. First one is when K very large. So you see that you see that the ratio is you have 1 over K squared. So when K very large, this is small, right? And so it's clear that when K large, the Boltzmann is a good approximation, is an approximation of free transport, right? Because when K large, the electric field is of order 1 over K, so it's small. So this is really the free transport. And the electric field decay exponentially as seen in the previous slide. Okay. When K is of order 1, you have a Penrose regime, meaning that plasma may or may not be stable. Okay, may or may not be stable. So you need you have a criterion. So Penrose in 1960 gave a criterion if and only if the plasma is unstable. Okay, in particular, that criterion satisfy. In particular, plasma is stable, meaning that equilibrium is stable for all monotones equilibria. Okay, the contributions of Penrose, in fact, to allow some bumps in tail, right? Some bump in tails, which was the controversy before that. But anyway, I just focus on monotone equilibrium So they are all stable in general sense. Okay. All right. And for K very, very small, you have Landau damping regime. This is a regime where the whole dynamics are driven by electric field, right? So you have this ratio, and when K is small, the whole dynamics is driven by electric field. All right. For Penrose stable regime, so you have equilibrium that are stable. Let's say you look at the plasma on torus, so you don't have small k. There's a breakthrough by Moore-Villani in 2011, where they prove nonlinear damping for analytic datum, and then the result was extended to by Birosian, Masmuri, and Moore to include some Jouvray datum. Okay, some Jouvray datum. And the key in their analysis is this bound, is this linear stability estimates, meaning that the bound L2 in time and L2 in K of the densities of plus boson bounded by the densities of the free transport. Okay, all right. The zero here is to indicate the free transport, and this is very deep inequality that they proved, and they be able to do that for nonlinear. Recently, with Emmanuel Grenier and Igor Rumyansky, we revisited these questions and recall that the resolvent is 1 over D, right? 1 over D, which is the ratio that I mentioned, the ratio between electric field and the transport, right? So we expand 1 over D by 1 plus 1 minus D over D. All right, there's some deep analysis behind this, meaning that we take equilibrium to be analytic, and for analytic equilibrium, this minus this 1 minus D over D, this ratio, can be extended all the way to the left of the complex plane, and we be able to obtain this L infinity based representation for densities of loss of boson. And precisely, density of loss of boson is density of free transport plus perturbations. With that representations, we'll be able to reprove the results, the mentioned results, the nonlinear mentioned results in a very simple way. Okay, so that was the first result, and the second result, we be able to construct a series of nonlinear echo solutions that initial datum could be very, very large in Sobolev. All right, and the key idea was that because you have this representation, so you could do everything in the natural pointwise norm, and right. So maybe let me move to the next regime. Let me move to the next regime. The point here is that you have these representations, and even for nonlinear, if you are in the analyticity class, all of these are exponentially damped, and because they are exponentially damped, so the loss in time, when you integrate in time and T minus S, it's suppressed if you have exponentially decay, right? And the key point is precisely that, meaning that because everything is exponentially decay, so by the time you actually have echoes, the electric field is exponentially small, so the interact is suppressed. Okay, that was the key point in the analysis to mention. Today I wanted to focus on Landau damping regime, meaning that the regime where K is very, very small, right? Which is not the case in all torus. And this is the case when electric field driven the whole dynamics. In this case, if you look at the dispersion relations, then you have two eigenvalues are approaching the imaginary axis. And so the previous analysis doesn't work anymore. because the dynamics is now completely different. There are two mechanisms underlying in this Landau damping regime. The first one is the plasma oscillations. Okay, when you look at dispersion relations, you have when you calculate the dispersion relations, you have the imaginary part of dispersion relations is approximately 1 plus k square. Okay, so plasma is time oscillations with the frequency 1 plus k square, right? And we be able to make use of this k square, which is this is exactly like dispersions in Schrodinger that you see, and we be able to make use of that dispersions to get the decay for electric field of order t minus 3/2. Okay, and this is the result that that we obtained with Daniel Nguyen and Perret last year, and we obtained that for general equilibrium, and about the same time, maybe a few days after, but there's the same results by Birosian, Masmouri, and Muho, where they prove that dispersive decay for Gaussians. Okay, for Gaussians. All right. Now the second damping mechanism, which is the original, visions of Landau, is the Landau damping, right? Which is precisely the transfer of potential energy to kinetic energy. The first instance of the first results along this line is by Placid-Schaeffer in 1994, where they be able to prove the L2 decay of the densities, and that's what they did. But right now, I wanted to focus on more precise results. What exactly the Landau damping in this regime? Okay, and this is the joint work with Emmanuel Grenier and Igor Runyansky. So this is what I wanted to discuss now. All right. So what is it? It's precisely the resonant interactions between particles and wave. Okay, between particle and wave. What is it exactly? It means this. So when you look at the dispersion relations, the imaginary part tell you about the plasma oscillations, which is actually known before. Then the key contributions of Landau is to compute the real part, right? The real part are in the dispersion relations. And the formula that he gave, or he computed, is this: is 1 over k square dv mu 1 over k. And the interpretations of that is that, you see, it's very important when you look when the particle velocities of the same order of wave velocities, and because the wave is obey Schrodinger type dispersion relations, and so the phase velocities is 1 over k, like 1 plus k square over k, and k is very small, so it's 1 over k. And when they are the same, then you look at if there are more particles, if there are more slower particles, then faster particles, meaning that when dv mu is negative, then you get Landau damping. And if there are more, if there are less slower particles than faster particles, then you should have Landau growth, right? And for physics, this is it means that if you look at a wave and you look at a lot of particles in front of you, then the particles would get energy from the wave, so the wave is damped. But if you have a lot of particles behind you, behind the wave, then the particles should give the energy to the wave, and you should have Landau growth, right? But because we are looking at in the case when equilibrium is monotone, it's all decreasing, so you get Landau damping. Note that the Landau damping is very, very weak for Gaussians. It's exponentially small, and it's polynomial weak for power law. So the faster decay in V, the weaker Landau damping you have. All right. And I wanted to discuss to make that precise in the physical space. Okay, make that precise in the physical space. Right. So this is the new understanding that we have. All right. So when you look at, so we obtain this decompositions of electric field, which is of the oscillation part plus remainder. And the remainder, you can calculate it, which is precisely of dx square of E0, where E0 is the electric field coming from the free transport, okay, and which is very fast. So remainder is very fast. And the leading term is the oscillations. And that oscillations, we can compute it more or less explicitly, okay, which is of this form in physical space. So you see, is decay is decay of order t minus 3/2, which is the dispersive, the right dispersive decay. You have the oscillations in space, just like Schrodinger. You have oscillation in time, and you have Landau damping. Okay, Landau damping. In particular, the subnorm is decay like t minus 3/2, and that is clear. And L2 norm is also decay. L2 norm is also decay. And for Gaussians, the decay for L2 norm is of order 1/log. Okay, 1/log t, which is now explicit from this formula. All right, from the formula. So the cartoon is that the art of Landau damping, you should see, is that if you look at in the space-time domain, and you wanted to see how electric field responds to the electrons, to the particles, then you see that when x is bigger than t, you should have very strong Landau damping, meaning that you should have the decay obey exactly what you see from the free transport. Within the light cone, within the x less than t, you should see the decay or dispersive decay like Schrodinger equations. Okay, you should have Schrodinger type dispersions. All right, and the genuine Landau damping that the formula that Landau discovered is very weak, and it should be in the regions just past the light cone. All right, and this is very mu. This is mu dependent. It's very weak for Gaussians and is stronger for polynomial. And I should mention that this is actually this formula that Landau discovered was a correction to the earlier work by Blasov. Right? All right, and you see that precisely it appears because of the resonance when the two velocities are the same. Right, two velocities are the same when particles and wave are the same. That for the for this result. That's for the picture of Landau damping. For the last slides, I just wanted to quickly mention some other results on nonlinear, also reasons on nonlinear damping. Is that when we look at the first results with Toan Nguyen and Rousset, when we look at the Coulomb interactions, but with screening, meaning that instead of looking at the interaction with 1/x, you have 1/x, but screening out large x, right? You're screening out large x. And in that case, because you're screening out large x, so you don't have the oscillations from some small k that I just discussed, and we'll be able to prove that Landau prove that results in 3D and higher in the similar analysis like Barros-Nogong in '86 when mu is equal to 0, right? And this result was proved earlier by Perosian, Sparkly, and Muho their method is using in the Fourier space, and what we do is in the physical space. The very recent results is with Sanchit Chaturvedi and Jonathan Nook from Stanford, and the result is precisely that we be able to prove Landau damping and enhance dissipations for the equations when you have the physical Landau collision operator, right? So when you have loss of Poisson adding the collisions, okay, and in that regime, so we'll be able to prove some Landau damping results when initial datum is more dependent on that would end my talk here. Yeah. Thank you.
Thank you very much, Toan. Thank you. This wonderful talk. So I guess we have time for a couple of short questions. Anything in the room?
Yes, we have a question, Jeremy. Go ahead.
Hi, Toan. I wanted to ask you about the ecos. So you construct solutions with ecos. I think this was towards the beginning of your talk. And I wanted to know for what the set of initial, is it a large, is it many solutions, few solutions, is it stable, is it the size, basically?
Thanks, Jeremy. That's a great question. So the way to view that is that Moore-Villani is the result where in Fourier space where the frequency is localized near zero, right? Actually localized at zero, right? That's Moore-Villani. So when you look at initial datum that is exponentially localized, now what we can do is that you can boot many Moore-Villani in the physical space, in the Fourier space, in that sense. Okay, so we allow to boot Moore-Villani not only at zero but also at arbitrarily high frequency in k and eta, and at each point we assuming that you have exponentially localized initial datum at that frequencies. Does that make sense? So instead of Moore-Villani at zero, you would put Moore-Villani everywhere in space, and because you allow to put everywhere in space, everywhere in frequency space. So if you calculate Sobolev norm, it's very large, right? Very large. However, because around each frequency point, you have exponentially localized around that point, then the echo interaction is still very weak. And that's how we be able to prove that result. Right.
But so I understand it's for few solutions, right? It's very special. It's not really stable around this solution. Or is it isolated solutions that you construct, or stable sets of initial data that lead to ecos? Sorry, I'm not sure if it makes sense.
No, that's okay. So the initial datum are prescribed, right? It's prescribed in the way that as an infinite sum of Moore-Villani sitting everywhere in frequency space. However, if you ask the questions whether that initial datum is stable or not, the question is not clear, right? And it likely that it will be unstable even for initial datum sitting at wait, the stable. Hold on, let me think about that. Okay, yeah. So of course, if you look at if you look at the initial datum, right? Of course, if you just look at even the initial datum that Moore-Villani just sitting at zero plus a small perturbations, that is not clear to be stable or not, right? That's not clear. And there's a result I should mention. There's a result by Berosians. He proved precisely that the solutions of Moore-Villani is unstable if you allow perturbations that are in Sobolev. And so in that sense, my solutions our solution that we constructed are not stable in SOPLEF because of the unmixed. Because you have mixing and then you have be unmixed and then that become unstable. Right.
Thanks.
One more question.
So this cartoon of the art of Landau damping, could you explain how it looks for the screened Vlasov-Poisson equation? What are the differences and how would the cartoon look?
Right. For the screen Vlasov-Poisson, you don't have Schrodinger wave. You don't have Schrodinger. You don't have that.
But the rest of the picture is identical, or
no? For screen Vlasov-Poisson, it's here. Maybe it's better to look at here, meaning that you look at the ratio between electric field and transport. For screen Vlasov-Poisson, you have 1 plus k square, and so the ratio always remains smaller than 1.
Okay, thank you.
And so the dynamics in screen Vlasov-Poisson is really governed by the free transport, exactly free transport. Okay, and because the dynamics of screen Vlasov-Poisson governed by the free transport, the nonlinear analysis was essentially the same like Bados-Dogon in 1986, right? Except that we have to understand the resolvent, which is exactly 1/d, and in there the resolvent is again, in the case of screen, the resolvent is again, you have this representations, free transport plus as exponentially small. Okay, exactly that, and that green function is still a perturbations of free transport, and that how one should see that results of the screening, and you screen out the Landau damping.
Okay, thank you. So I would suggest again, in the interest of time, that we thank Toan again for the nice presentation, and move on to the third speaker of this. So Luis, hi. Perfect. So
hello.
Hi. So are you ready?
I guess. Let me see.
Okay. Great.
Let me open the file. All right.
Right. So the third speaker is Luis Silvestre from the University of Chicago, and he will speak on the conditional regularity estimates for the Boltzmann equation.
All right. Thank you. Thank you very much for the invitation. So I'm going to be talking about the Boltzmann equation. So it's good that I'm talking. It's so usually very difficult to talk about the Boltzmann equation in any math conference because you have to spend a lot of time explaining what the equation is, and people still take some time to get used to it. But it's good that I talked about it right after I talk about the Vlasov-Poisson system. So you're already used to the idea that we have this density function of particles with respect to their position and velocity. So this is in the Boltzmann equation, this is modeling the state of some sort of dilute gas. You can describe the gas by the microscopic structure of where each particle is and where the velocities are. You can describe it in terms of the hydrodynamic equations like the compressible Euler equation, like in Tristan's talk earlier on, or the intermediate scale is in kinetic equations where you have this density function of particles with respect to the position of velocity, and we have an equation of how it evolves in time, right? So in the Boltzmann equation, I have the transport equal to this collision operator, to the Boltzmann collision operator. So compared to the Vlasov-Poisson system, I'm neglecting the electric field, and I'm taking into account the local interaction of particles by essentially collisions, right? So in the Boltzmann equation, the collision operator has this form. So it's it's a quadratic operator on F. It acts on the velocity variables, meaning that here F, F star, F prime, and F prime star are values of F at different velocities, but at the same time t and position x. So it's like at the same position in space, I'm evaluating F at different velocities, because basically this is the result of collisions. You can think about it this way. So I'm looking at how many new particles are generated with velocity v and how many are lost. So they're being lost because a particle with velocity v is colliding with a particle with velocity v star. V star is one of the variables of integration. And because they collide, particles change their velocities, and I lose particles of that velocity v. That's why I'm subtracting. But then particles with different velocities, v prime and v prime star, are colliding, and they're creating new particles of velocity v. This kernel here, capital B, is the rate by which the collisions of particles with velocity v prime and v prime star become particles of velocities v and v star. The velocities v prime and v prime star have some restrictions because they have to satisfy conservation of momentum and energy. So they are parameterized with respect to certain spherical variable, and this kernel capital B has several forms depending on modeling assumptions. So if you think that particles are like billiard balls that bounced against each other perfectly, then you would have certain kernel capital B. If you think that microscopically the particles repel each other by some sort of power law potential, then you get these different kernels that in the kinetic literature they typically refer to as the non-cutoff kernels. So you see there are these parameters gamma and S. In the physical models, gamma and S are related, but here we're taking them as being two different parameters. So, I mean, it's unclear what's the right physical model, and it may depend on situations. So there are, in mathematics, we take different, almost any sort of kernel capital B, and we study the equation with them, okay? So in my talk, I'm gonna be concerned with regularity estimates, and they apply for the non-cutoff kernels. That is for this kind of kernels, the one you get when microscopically the particles repel each other by some power law potential. So there are many questions that one can study about the Boltzmann equation. One of the most popular one is to study asymptotic limits, which is not what my talk is about, but it's good to keep in mind that if you look at the Boltzmann equation, you make and you enhance the collisions, then the solution of these equations, at least formally or informally, converge to something that is a Gaussian in velocity at every t and x. And they would be the Gaussians so that if you look at the mass density, that is, I mean, if I integrate f in v, and then I look at the velocity density and the temperature density, then these three quantities in the limit as epsilon goes to 0 become solutions of the compressible Euler equation, right? So these are in a way, the macroscopically visible quantities with respect to each solution of the Boltzmann equation. And, you know, one is reasonable to expect that in some large scale asymptotics, they will be approximately a solution of the compressible Euler equation. And that's an interesting thing because the compressible Euler equation, as we saw in Tristan's talk, develops singularities in finite time. So what should we expect for the Boltzmann equation? So let's talk about the Cauchy problem. Suppose that we have an initial data that is smooth, let's say periodic in X, so that we don't have any physical boundary to worry about. And then it decays, it has some fast decay as velocities go to infinity. So we wish we could solve the Boltzmann equation with initial data f0. And by solve, I mean finding a classical solution for all times that remain smooth, right? Is this problem solvable, or does it develop singularities in finite time? So we don't know. This is a major open problem that seems to be very difficult. So what should we expect? Well, as I said, in certain large scale, the solution of the Boltzmann equations behaves similar as the solution of the compressible Euler. And the compressible Euler does develop singularities. And like in Tristan also today mentioned that there are two different types of singularities for compressible Euler that are very different. The shock type singularities and the implosion singularities. Now, the shock type singularities are basically you have a bulk of fluid coming in one direction that is crashing against another bulk of fluid coming in the opposite direction. So then a discontinuity emerges from the flow of the equation. And a discontinuity is a singularity that exists because in the Euler equation, the hydrodynamic description of fluids, the velocity is a function of time and space. And a function cannot take two different values at the same time. So when you have two different velocities at the same point, it's thus creating a discontinuity in the velocity. But in a kinetic description of the fluid, we have this density function. And in the density function, F is a function of X and V, and it has no problem in having different velocities coexisting at the same point in space. So shock singularities are not really a type of singularities that would be, that is not something that will create a singularity for a kinetic equations, right? So the fact that the Euler equation creates shock singularities does not mean or does not suggest that we should expect any kind of singularity like that for the Boltzmann equation. Implosion singularity is a different story. In the implosion singularity, the velocity, the density, and perhaps the temperature are becoming infinite at one point, right? And a priori, there is no reason to rule out an implosion type singularity for the Boltzmann equation. So there is it would be a fair guess to expect implosion type of singularities to exist for the Boltzmann equation, even though they haven't been constructed yet, and it doesn't seem to be an easy problem to either prove or rule them out. But a priori, I cannot rule them out. So it seems that there is a very good chance that implosion singularities exist for the Boltzmann equation. And I said that this talk was about regularity. So in which sense, what are we going to prove? So even if implosion singularities exist, what remains to be shown is if that's the only type of singularity. So the question is there any other type of singularity that is more kinetic in nature that emerges from the flow of the Boltzmann equation? If you have a solution of the Boltzmann equation that, let's say, these hydrodynamic quantities, these macroscopically observable hydrodynamic quantities don't do anything funny, then would the density function create a singularity because of the kinetic nature of the equation? And that's the answer that we're going to answer in the negative. That's the question that we're going to answer in the negative. So what we do is we prove that the solution of the Boltzmann equation in the non-cutoff case are smooth, provided that the hydrodynamic quantities stay bounded and away from vacuum. So it's a conditional regularity result because this is conditional to the hydrodynamic quantities staying bounded. That condition is effectively ruling out the implosion singularity. So we make that condition to say an implosion singularity does not occur anywhere, and conditional to that, the solution will remain smooth. Okay? So you can interpret it as saying that any singularity in the Boltzmann equation will be visible with respect to these hydrodynamic quantities. And in a way, it's saying that nothing else, no other type of singularity will exist in the Boltzmann equation other than the ones that, in a way, should be observable in the hydrodynamic equations. All right, and like I said, unconditional regularity, that is proving the well-positiveness of the Boltzmann equation without any condition like this, seems to be a completely out of reach question at the moment. So let me do some quick review of earlier results about regularity for the Boltzmann equation. So one dramatic simplification that one can make for the Boltzmann equation is to look at the space homogeneous problem. That is, looking for solutions F that depends on T and V only. That is, if your solutions are homogeneous in space, what is going to happen with the solution as the Boltzmann equation evolves? In here, of course, for the hydrodynamic problem, a constant solution will be completely trivial. It's just stay the same forever, right? So the macroscopic quantities don't do anything in the space homogeneous problem. But it makes sense to study the Boltzmann equation to see how the distribution of velocities evolves. And at least for some range of parameters, the problem is fully understood. And it's known that for any initial data, even if for any reasonable initial data, even if it's very rough, the solution becomes immediately C infinity. Then if the solution is sufficiently close to equilibrium, there is also, you can also prove that the solution, there exists smooth solutions for all time, and that it converges exponentially fast to equilibrium. In this case, equilibrium are the Maxwellian solutions that are Gaussians in velocity that are constant in space. And there was, this is the most relevant result compared to our result. That is also a conditional regularity result, but with a very strong condition. So if you know that the solution multiplied times any power of V is in H5 with respect to space and velocity, then in these papers, they proved that the solution was C infinity. So it's also a conditional regularity result, but with a much more stringent condition than the one we have, right? So let me state the theorem that we have. It's joint work with Cyril Imbert. So we take a solution to the inhomogeneous Boltzmann equation in the same range of parameters for which the homogeneous problem is known to be well posed. And we assume that these quantities, that these four inequalities hold. That is, the mass density is bounded below and above, the energy density is bounded above, and the entropy density is bounded above. So we assume that these macroscopically observable quantities are under control. This bound above, the bound below for the mass density is because we want to avoid vacuum. And the bound above for the entropy is a little bit stronger than assuming that the temperature density is bounded below. So we also want to be away from zero temperature, right? Assuming that the entropy is bounded above is a little bit stronger than assuming that the temperature is bounded below. So it basically, it tells you that the density function F does not concentrate on sets of measure zero. So under these conditions, we get a priori estimates for all derivatives of, in respect to all variables that decay faster than any algebraic rate as the velocity goes to infinity, right? So it's a conditional regularity result, all right? So this is our theorem. So I'm gonna discuss some of the consequences of this theorem. One way to see this is a continuation criteria. If you have a smooth solution that remains for a certain period of time, then the solution will be, we will be able to continue this solution for as long as the hydrodynamic quantities stay under control. That means that if the smooth solution ever ceases to exist, then one of the hydrodynamic quantities has to be going to plus infinity, or maybe the lower bound on the mass density goes to zero. However, I mean, there are some further results on continuation criteria that show that if the solution ceases to exist at time t, then either the mass density or the energy density go to plus infinity. That's a paper by Henderson, Nelson, and Tarfulea that builds up on this work. Another consequence is with respect to the convergence to equilibrium. There is a well-known result by Cédric Villani and Laurent de Villers that they show that for any solution of the Boltzmann equation, conditional to state uniformly smooth for all time, then the solution converges to a Maxwellian distribution as time goes to infinity. The Maxwellian distributions are the stationary solution of the Boltzmann equation. So this is a result that's saying that the solution of the Boltzmann equation converge to equilibrium as time goes to infinity. But it's also a conditional result, and it's conditional to having uniform regularity estimates that are uniform for all time. You know, it's a very difficult thing to be conditional on, right? Because it's a very strong condition. But then our result provides those uniform regularity estimates, but it's conditional to something much weaker, which is that the hydrodynamic quantities stay bounded, all right? Another consequence that I want to discuss is that the conditional regularity results trivialize the construction of global solutions near equilibrium. So why is that? So I mean, how does it work? So what I'm saying is, if you take a conditional regularity result of Villani and de Villiers, you combine it. No, the converges to equilibrium result by the Villiers and Villani. You combine it with a conditional regularity result and any short time well posedness result that you can prove with respect to any norm, that immediately implies that global smooth, that if the initial data is sufficiently close to equilibrium with respect to whatever norm the short time well posedness works, then you have global smooth solutions. Why is this? So let me give you some rough explanation of how this works. Forget about the conditional regularity for a second. If you have convergence to equilibrium and you have short time well posedness, it's reasonable that you would expect that if the initial data is sufficiently close to equilibrium, there's going to be a global solution. And the intuition is the following. If the solution lasts for sufficiently long time, the convergence to equilibrium is going to push it next to the equilibrium solution. It's going to push it very, very close to the equilibrium solution if the solution lasts for sufficiently long time. Now, if you have short time well posedness, it means that if the initial data is very, very, very close to equilibrium, then it's going to stay close to equilibrium for some period of time, depending on how close it is to equilibrium initially, right? So intuitively, if you start sufficiently close to equilibrium, the solution is going to last for a very, very long time. But if it lasts for so long, the convergence to equilibrium is going to push it back close to equilibrium, as close as it started. So convergence to equilibrium combined with short time well posedness seems to imply that if the initial data is sufficiently close to equilibrium, we have global solutions. Except that it doesn't quite work. And the reason why it doesn't quite work is because the convergence to equilibrium result is conditional to having uniform regularity estimates for all time. And the short time well posedness is with respect to some norms that are weaker than C infinity. So the norms by which you have closest to equilibrium, by which you have short time well posedness, are not enough to ensure the convergence to equilibrium. And that's the gap that is filled by the conditional regularity result. If you have short time well posedness with respect to any reasonable norm, then for as long as the solution holds, it's going to stay relatively close to equilibrium with respect to some weak norm that is going to ensure the hydrodynamic bounds that I mentioned before. And then the conditional regularity gives you regularity with respect to all the all derivatives, and that ensures the convergence to equilibrium, right? So the conditional regularity sort of fills the gap that makes this proof look like the ODE proof of asymptotically stable equilibrium, right? So we implemented this proof in a recent paper with Stan Nelson with respect to the L infinity norm. So basically it works for any norm for which you can prove short time existence. So let me go back to the Boltzmann collision operator. And what I want to do is I want to explain how to understand the Boltzmann collision operator as an interdifferential equation, as a nonlinear or as a quasi-linear interdifferential equation. You know that in the last decade or two, there has been a lot of activity in studying non-local equations that are like elliptic or parabolic equations with operators that are some nonlinear version of the fractional Laplacian. The Boltzmann equation fits into this category if we are willing to move around terms a little bit, and that's what I want to explain. So this is the Boltzmann collision operator that I wrote in the first slide and the way it's usually written. So there is this kernel B that I'm going to be taking the ones of the non-cutoff kernels, but a priori the derivation that I'm going to make now is for any kernel B. So what I want to do is I want to add and subtract this term, right, in order to split the Boltzmann collision operator into this first term and that second term. And of course, I'm going to take common factor for each of them to simplify them. All right. So in the first term, so I'm taking the common factor f of v prime star. And in the second term, I'm taking the common factor f of v. f of v is the variable that I'm evaluating, so it's independent of the variables of integration. It's going to come out of the integral. Whereas this thing is going to become a kernel. So f of v comes outside of the integral, and this one is sort of like a kernel that depends on the function f. So I'm going to write k sub f of vv prime. So one can compute exactly what this kernel k is by integrating f v prime star times b along all the possible v prime stars for each possible value of v prime and v, and doing the necessary change of variables here, right? It's sort of a messy change of variables. In kinetic equations is known as Karleman coordinates, but there isn't really any mystery here. I mean, it takes a few minutes to work it out, even if you've never seen it before. So this kernel, of course, depends on the function f, because it's the integral of f v prime star times this b along those variables. So that's why I'm saying this is like a quasi-linear equation. You know, if you take a parabolic equation that is quasi-linear, what is a parabolic equation that's quasi-linear? It's like a linear parabolic equation, but the coefficients are allowed to depend on the solution. So the coefficients in front of d square of u depend on the solution itself. Here I have an integral differential equation, an integral differential operator with a diffusion kernel that depends on the solution itself, right? So that's kind of like a quasi-linear integral differential equation. It's a quasi-linear non-local equation. And that's where non-local equations enter the picture, right? Non-local equations or interdifferential equations that were studied in the last 20 years were always involving operators like this one, where k was some given kernel satisfying certain hypotheses. And there are results like Dichochi-Nash-Moser, like Schauder estimates, like Krylov-Safonov estimates for parabolic equations involving operators like this one, and under certain hypotheses of the kernel k. But now we have to see what kind of kernel we are getting. Are we getting any ellipticity constraints of this kernel? What is it, right? So I'm going to give you a formula for the kernel k, which depends on the function f, that holds when the collision kernel b is the ones, the so-called non-cutoff collision kernels. So for the non-cutoff collision kernels, this kernel k is going to be exactly the kernel of the fractional Laplacian multiplied times some factor, and the factor is the following. If you have the velocities v and v prime, you have to integrate f along the plane through v that is perpendicular to the direction vv prime. You have to integrate f times this weight. So that integral of f is exactly the factor in front of the fractional Laplacian. Now, if you go to the original literature in integral differential equations, common hypothesis for kernels to be considered uniformly elliptic of order 2s would be that they are comparable to the kernel of the fractional Laplacian, right? This is relatively common in the literature of integral differential equations as a hypothesis. We are not really going to get that unless we know a lot of information about the function f. I said that my only hypothesis on the function f was going to be that the hydrodynamic quantities are under control. That is, the mass density, energy density, and entropy density are going to be bounded. And I want to get ellipticity conditions on this kernel based on those conditions only, right? So this is an integral of f along a hyperplane. If I know something about the integral of f, the second moment of f, or the entropy of f, I cannot get any pointwise bound from either below or above for this factor, right? But I can get bounds on average. So these are exactly the bounds that one gets based only on the hydrodynamic constraints. So by construction, the kernel is going to be symmetric in this way. K of v, v plus w is going to be k of v, v minus w. This is, I'm saying in a non-divergence way, because the integral differential operators with this kind of kernels are the integral differential operators for which one can use the techniques that come from elliptic equations, elliptic operators in non-divergent form. I mean, it's a type of reference to the integral differential literature. So the lower bound, that is the lower bound for the kernel with respect to the kernel diffraction Laplacian, is gonna hold only on a cone of directions. Why is that? I mean, look at this factor. This factor is the integral of f. If we know that f has a finite entropy, it's not concentrated on a set of measures 0, it's also away from vacuum, so it's going to be large. F is going to be large at many, many points in measure. So there's going to be plenty of directions in which this plane will hit the points where f is large. And that's why you have a cone of directions in which the bound below holds. But we don't know in which directions they are. We just know that these directions have positive measure, right? The upper bound is going to hold only on average. So that is, if we integrate over all directions, we get the same upper bound as if we had the kernel of the fraction Laplacian. And then we have this cancellation. So it's not a symmetric kernel by flipping the variables, but the error is sort of lower order. So let me say something about the conditions. So this is a conditional regularity result. Whenever you hear a conditional regularity result, the things that you try to associate with other conditional results that you know of. So it would ring a bell to think about Navier-Stokes equation, the Prodi-Serrin conditions, and conditional regularities like that. In those results, the conditional regularity is based on scaling. The Prodi-Serrin condition for Navier-Stokes effectively implies that the diffusion is stronger than transport. Here, it's a different mechanism that is taking place. The condition is for the kernel to be elliptic. So when I made those conditions on the hydrodynamic quantities, it's because I want this kernel to satisfy these two bounds, the lower bound on the cone direction and the upper bound on average. There is no scaling, or there isn't really any competition between diffusion and transport here. What I need is to have diffusion at all. What I need is the kernel to have some ellipticity to begin with, and that's what the conditional bounds give me, right? So it's not a matter of scaling here. All right, so let me tell you something about what are the ingredients in the proof, because the proof is long and it contains several steps. The first step is an L-infinity estimate. That is a conditional to the macroscopic quantities I want to show. I want to obtain an L-infinity bound for the solution that is independent of the initial data, right? This L-infinity estimate is proved specifically for the Boltzmann equation, but the proof uses some ideas that originated in the study of integral differential equations. And in fact, the idea that goes into this L-infinity estimate resembles very much the nonlinear maximum principles as in the paper of Vlad and Peter Constantine. Second step is a weak Harnack inequality. So you know there is this theorem of Dichochi, Nash, and Moser that tell you that uniformly elliptic equations in divergence form are Helder continuous with respect to some estimate. There is a parabolic version of that result as well. There is a kinetic version of that result as well. That is transport equation equal diffusion in velocity. And that's more recent, right? And what we do with Cyril Imbert is we do a kinetic integral differential version of the theorem of Dichochi, Nash, and Moser. That is, we have transport equation equal diffusion, integral differential diffusion in velocity, right? And under those conditions, we can reproduce the theorem of Dichochi, Nash, and Moser that gives us Helder continuity in all variables. So even though the diffusion is in the velocity variable only, we get regularity in all variables. So notice that this weak Harnack inequality is not specific for the Boltzmann equation. It's for any equation that is transport equal to integral differential diffusion. Now, the Boltzmann equation happens to have that structure. We have that the right-hand side is an integral differential diffusion with respect to certain kernel that satisfies some conditions. And whatever that kernel is, these conditions are enough to give us Helder continuity applying the Harnack inequality. So this is more or less like, it's very common when you study nonlinear PDEs, that let's say you have a quasi-linear parabolic equations, your first step is to use the Church-Nash model, which is, superficially a linear result, but with very little assumptions on the coefficients. So here we have a Weak-Harman inequality, which is superficially a linear result, but with almost no assumption on the kernel. So we can apply it to any solution, right? Then we have Schauder estimate, which is also a generic result for kinetic interdifferential equations. That gives us further regularity. Once we know the Helder continuity of the solutions, we have some regularity. We infer some regularity for the kernel as well, and that gives us higher regularity on the solution. Then we have pointwise decay estimate that tells us that the solution decays faster than any polynomial. This is a joint paper with Cyril Imbert and Clément Mouchot. Then we need to study the asymptotic as v goes to infinity. So there is certain change of variables that adjust all the ellipticity of the kernel, and that allows us to compute exactly how the regularity deteriorates or improves for large velocities. And once we have that, we just bootstrap the Schauder estimates, and we get higher and higher regularity. Okay? So those are the ingredients in the proof. Of course, each one of these is sort of a different story and a different paper in a way. So let me conclude by just giving a list of open problems that remain open, which are a lot more than the ones that are solved. So like I said, there was a paper of Chris Henderson, Stans Nelson, and Andrei Tarfolea that they proved that if the mass and energy stay bounded from above, that's enough to get a continuation criteria. But a priori, it's an open-ended question. What's the weakest continuation criteria one can get? One can think that if you have a mass density and energy density, some integral condition, some sort of Prodi-Serrin type LP condition should suffice, but it's harder to work with that. There were these parameters for the non-cutoff kernels, and we take them in this range, gamma plus 2s between 0 and 2. A valid question is to study what happens outside of this range. For gamma plus 2s greater than 2, there is some work by Stans Nelson and Stephen Cameron. But for gamma plus 2s negative, the proof of the L infinity bounds fails even in the space homogeneous problem. So this is actually a very difficult open problem. Very interesting as well. Cutoff case, we didn't do anything. Then bounded domains is an interesting continuation of this work, which is we did periodic boundary condition in space. One can study the same problem in a bounded domain with some physical boundary condition on the boundary. And then, of course, the obvious open question is to do unconditional regularity for the inhomogeneous non-cutoff Boltzmann, that is, take any smooth initial data and try to prove that there exists a smooth solution for all time with no condition at all. And my advice is that you solve first the Millennium problem for compressible Navier-Stokes as an easier warm-up problem, because this problem seems to be very, very difficult. I would guess that I wouldn't completely rule out the fact that someone may come up with an implosion singularity for this problem, but even that seems very complicated. Proving regularity, unconditional regularity, seems completely out of reach. So anyway, I guess that it's a good time to finish my talk.
Thank you very much, Luis, for this very nice overview. So I think we have time for a few questions, short questions. If there is any in the audience.
There is one, yes.
Please.
Okay, do you hear me?
I hear you.
Okay, thank you. So thank you for this very nice talk. Actually, I have a question. Perhaps I missed that in your presentation. What do you mean by far from the vacuum? Do you mean that the mass is bounded from below, or there is a profile from below?
No, the mass bounded from below. It's this lower bound here.
Okay, okay. And so do you know
what I mean by far from vacuum.
Okay, and so do you know, so it's the, let's say, natural second step of the equation. Do you know if you can obtain this in the Cauchy theory for the Boltzmann equation?
What do you mean the Cauchy theory?
The fact that the mass keeps bounded from below.
Well, I mean, And conditional result is completely impossible. If you give me a generic initial data, then of course I cannot prove any of these inequalities, not the mass, neither the away from vacuum, but none of the others either. Now, if you give me a reasonable initial data and you can prove that the mass is bounded above and the energy is bounded above, then you can prove that the mass is bounded below by a bound that deteriorates in time. That is the paper of Henderson, Nelson, and Tarfulea, right? Of course, if the initial data is close to equilibrium, everything is trivial, right? So if the initial data is close to equilibrium, everything is trivial. But if the initial data is generic, the four inequalities seem to be unprovable at the moment.
Okay, and then just a very last question about, let's say, this aspect of the theory. So concerning the non-cutoff Boltzmann equation, is it known that you keep the positivity of the solutions, or?
Oh, yeah, of course. The positivity, yes. I mean, if you look at the, you have transport, right? Equal to Q. And look at what Q is. Q is, this is positive. And then this is a interdifferential operator with a maximum principle. So it can, if it starts larger or equal than 0, it can never go below 0, because if f of v was ever 0, this operator would be strictly positive. Right?
Okay, thank you very much.
Yeah.
I don't see other question here.
Maybe I'll ask a question, Luis.
Yeah.
So you mentioned a lot of open problems at the end, and I just wanted to ask you, so you finally now developed a good regularity theory for Boltzmann. And sometimes when you have a good regularity theory for a limiting system, you can get better results in which the system is approximated. So the question is, do you think that your theory has any consequences for this Landau program of deducing Boltzmann from particle dynamics?
I'm not sure. So the problem is, you know, there are different asymptotic regimes in which you get hydrodynamic equations from the Boltzmann equation. So I wrote the one that leads to compressible Euler. There is a different asymptotic regime that is actually by perturbations of equilibrium that leads to incompressible Navier-Stokes.
But that's not what I'm asking. I'm asking to get Boltzmann as a limit from particle dynamics.
Boltzmann as a limit for particle dynamics. No, that I never thought about. So Boltzmann as a limit of particle dynamics,
because
I don't know, because there is a,
when you have mean field limits and you want to deduce, let's say, Euler, the regularity theory for Euler is very important to actually allow you to pass in the mean field limit. And now you have a good regularity theory for a limiting system, which is Boltzmann.
Right.
In principle, you could imagine that this would have a consequence for this Landau program.
Yeah, perhaps, I don't know. So because there is this result of San Ramon works on that. I've heard talks by her, but they were always about the cutoff Boltzmann.
Sure.
I don't know what's
and
that.
You know exactly why, right?
I don't even know what's because of this, because the kernel is very hard to control, right?
Anyway, this was just an open-ended suggestion.
Yeah, no, I don't know. Let me tell you that I haven't really worked on asymptotic limits, either one, but the one that you are asking me about is the one I know the very least, which is from particles to Boltzmann, right?
Wanted to make your day interesting.
What? Yeah. And of course, what I was going to answer, which is not your question, is about what happens from Boltzmann to hydrodynamics, about whether this regularity could help you in any way. And the problem is that there is this parameter epsilon, and our regularity results are not quite uniform with respect to this epsilon, right?
Naturally.
But anyway.
Thank you very much. I think this is a good place to stop. So I want to thank all the three speakers of this session and all of the audience for attending and all the questions. Thank you very much.